Okay, in this final lecture of chapter 1, do one more example of fitting a nonlinear curve to data, and then we'll just have a little small summary of this chapter. Okay, let's look at this question. In order to predict the number of blows n required to pile drive to a certain depth in a given soil, the following recordings were made. So we would have seen this data actually in an earlier question. So a way to do this is to model the relationship between n and d using this. So what have we got? Write the relationship in linear form. Okay, find the best constants a and b. Well, that'll be via m and c, and hence estimate the number of blows required to reach a depth of 2.5. It says 3 significant figures for all calculations. That should make things easy, but we might get a little bit of rounding error. Right, so the first thing is to write the relationship in linear form. So we have n is equal to a times e to the power b d. Right, so we want to turn the multiplication into addition, so we're going to take the log of both sides. This is something we've seen previously. So we get log of n is equal to log of a times e to the b d. And now the log, why did we do this? Because log turns multiplication into addition. And now we know that exponential and natural log are inverses. So if you have an exponential and you do a log, it gets rid of the exponential, you're just left with bd. So you have log of a plus b times d. And we're hoping to get things in the form y equal to mx plus c. Now the thing on the left is always going to be your y. So the log of n is your y. Now we need a constant times a variable mx. Now it's because the constant b is in here, we know that it's a constant, but actually moreover you know that d is a variable because you've got data for d. D changes, d is variable. So this is like your x, mx. And finally log of a is the c, so you got y is equal to mx plus c. So what we're going to do is we're going to find the curve of best fit of the best curve y equal to mx plus c to the data, that is d and log n. So the normal equations, well, as before, the multiplier for c is just 1, and the multiplier for m is x. So the multiplier for c is 1, multiply everything by 1 and add up. So multiplying by 1, of course, makes no difference. So it's add up y, add up mx, take out the constant m, add up c, and then the multiplier of m is x. So I get x by y, add up, mx by x, mx squared, add up, and c by x, and add up, take out the common factor c. So that's where we are. So we tabulate. So we need to add up y, so we need to add up log of n. So we'll say y is log of n, and if you take the log of these numbers here, you get these numbers here. So that's the log, that's the y. Add them up, you get 20.7. Okay. You also need to add up the x, so you want x. Now the x is the same as d, so I just exactly copy the 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, add up, I get 10. From here I need to add up x by y, so I calculate x by y. So I calculate 0 by 2.3, 1 by this, 2 by this, 3 by this, 4 by this, and add up, I get 50.6. And finally I have to add up x squared. So I square these x's, 0 squared, 1 squared, 2 squared, 3 squared, 4 squared, and add up. The only thing that's missing is adding up the c. Now if you want, it's like c, 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 and adding up 5 c's gives you 5c. Okay, so now we want to write down the normal equations, and the way I'm going to do it is multiple of m plus multiple of c is equal to constant, do that twice. So the multiple of m is add up the x, which is 10, so I have 10m, plus add up the c's, which as I just said is c, 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 5c, equal to add up the y's, which is 20.7. Okay, and then the other one, add up the x squared times m, that's 30m. These might be easy to solve, probably won't need a Cramer's rule. But I do recommend the Cramer's rule when there's decimals, and maybe if you want to get used to it, even when you don't need the Cramer's rule, maybe use it. Plus c times add up the x, and the add up the x we found already is 10. Equal to add up x by y, which is 50.6. Yeah, these look kind of handy. I could multiply maybe the first equation by minus 2. So I get minus 2 by 10 is minus 20m. Minus 2 by 5c is minus 10c. And then minus 2 by this will give me minus 41.4. Add these together. And I get 10m is equal to, no, just be careful with these. I lost my nerve. I'm normally not too bad. I'm gonna have to go back to, so like the issue is here, like look, I can do this. It's 8.6 plus this, it's gonna be 9.2. My concern is, you know, it's very easy to put something into the calculator, press equals, it's gonna be 9.2, but it's wrong. And if you keep using the calculator, you'll lose a sense for what the number could be. I mean, you know it's going to be about 9. If something goes wrong, you won't get that. So try and avoid the calculator if you can. Now what are we going to do? Now there's a good bit to go here. It looks like we're just finding m and c, but actually we need to find a and b. First of all, anyway, we want to find m. It's multiplied by 10. We want the inverse of multiplying by 10, which is dividing by 10. So do that to both sides, it'll get rid of the 10 here, and 9.2 divided by 10 is 0.92. So that's something, and maybe we'll substitute that into this, and hopefully find c. So 10m, 10 times this, well we know it's 9.2, plus 5 times c is equal to 20.7. I'm looking for c on its own. I got this plus 9.2 in the way, so if I take that away from both sides, I'll have 5c on its own. So 5c is equal to 20.7. Take away 9.2, which is coming out as 11.5. And I want to get rid of that multiplied by 5. The inverse of multiplying by 5 is dividing by 5. If I do it to both sides, they stay the same. I get c is equal to 11.5 divided by 5, which is 2.3. Now that what that gives you, you could run with if you wanted. You've got, say, y is equal to m x plus c, but like this is quite abstract. I mean, we're talking about depths, number of blows. So what you have to do now is you have to kind of work back into what you had. Like we shouldn't be writing y and x, we should be writing n and d. So really what you need to do is look back here. So m is equal to b. So if we found m, we have this is in fact equal to b. So that's good, we have found b. And c is log of a. So where are we at? We are as follows. Log of a is equal to c, that's here, and c is equal to 2.3. And now you got to say you want to find a. What is the inverse of ln? The antilog, I think you call it. So it's the exponential function. So do the exponential function, apply that to both sides. You get a is equal to e to the power of 2.3. And 3 significant figures. I'll just go into the calculator for this. 3 significant figures, 9.97. And so the model is in fact that the number of blows required to get to a depth of d is equal to a, which is 9.97, times e to the power of b, which is 0.92, times the depth. And you can check kind of roughly, is this looking good, by substituting in a depth of 0. And if you do, you get e to the 0, which is 9.97. It's approximately 10. Now, it doesn't have to be that accurate, because there can be more errors in the measurements than that, but how bad? So in the end of that question was, so write the relationship in linear form. We did that. Find the best values of a and b. We did that. There's a, there's b. Then we kind of wrote down our model. And then the last thing is, hence, using this mathematical model, estimate the number of blows required to reach a depth of 2.5. So I'm just going to substitute 2.5 into this. So n of 2. This is like f of x. It's not here, but it's kind of implied. So the number of blows to get to a depth of 2.5 should be approximately given by our model, 9.97 times e to the power of b times 2.5, and approximate this to three significant figures, and it's a number so we don't have units. 9.97 by e to the power of 0.92 by 2.5. Now we did this with Lagrange interpolation a good few lectures ago, and we got it 105. So here we're getting in fact 99.4, which now should we round to 99? There's an argument yes. I'd actually say, for being a little bit strict, to get to 2.5 meters, well, I suppose like maybe you don't want to go deeper. You could round it to 99 or 100. I think either is good. I'm actually going to round to 100 because 99 is not enough. Whereas if you do 100, according to this model, obviously it's quite rough. This would only be for estimating how long would it take. So like you got to bore 20 holes or whatever. It'll take 20 by 100, whatever that is, 2,000 blows to do the whole site. And it's just a rough thing. Like you can talk about errors after that if you went to level 8. But for us, we're just going to come up with the raw figure. Yeah, happy enough with that. I don't know if we got a graph on the next page. Yeah, we do. So here we see the number of blows. As it goes deeper, you need more and more blows. Because as I said, perhaps as you go deeper, the ground compacts and you need more and more blows to go 1 meter further. Now, one thing you might have seen, certainly if you get the manual, is there's actually more worked examples than this. So you can see some of these here. I'm just going to go through. So there's one there. There's one there. There's a third one there. There's a lot of these worked examples, which might be helpful to you in your either your learning when you're doing exercises or when you're doing the assessments. So there's three of them. Here's obviously your exercises. I'll be trying to get you to do a lot of them. And I'll just have a small little chapter summary. So the normal equations, now actually what this is, these are the formulas that I used to put on the exam paper. I used to put the normal equations for y to mx plus c. Obviously it's slightly more complicated in general. I think we're going to see that on the next page. But for y to mx plus c, where the multiplier of c is 1, gives you this, and the multiplier of m is x. So multiply everything by x and add up. Then the log stuff, logs turn multiplication into addition, powers into multiplication, and log is the inverse of exponential. I'm not even sure am I going to examine Lagrange interpolation, but when it comes to that day, here's the formula. Okay, what's we got? So you still want this knowledge. So Lagrange interpolation is the fitting of a quadratic or parabola. So it goes through 3 points, and then you sub in the value of x you want. There's an extra line there, doesn't matter, and it'll give you the thing. Least squares is you have, now here this is theta 1 is like the multiplier of a, theta 2 is like the multiplier of b. So you have a curve of a certain shape, you want to fit it, you've got data, you want to fit the data to fit the curve in such a way that it minimizes the sum of the squares errors. How you can do that is by doing some differentiation and finding that these are the normal equations. The multiplier of a here is theta 1. Multiply everything by theta 1 and add up. And then go back to the start, multiply everything by theta 2 and add up. The correlation coefficient gives a measure of the goodness of fit. The closer to plus or minus 1, the better the fit. Nonlinear least squares or log linear is fitting a not necessarily linear curve to data. To fit a nonlinear curve, you must first get in the form y equal to mx plus c using logs. Tabulate the new x and y. Look at your normal equations. You might have to tabulate x, y, and x squared. Solve for m and c, and then convert back to the original constants. So that's everything in chapter 1.